Dear students, welcome to the third lecture. So last lecture we have seen that second countable implies first countable, second countable implies separable, and second countable implies Lindelof. Now today we shall see that the converse of these statements is not true. That means we shall give one example which is first countable, separable and Lindelof, but that is not second countable. And the example is RL, that is the real line with lower limit topology. Now first of all we shall show that this is first countable. Now claim RL is first countable. Okay, that's mean for each point we have to find one basis at the point x, right? So it is very easy to construct the basis for any point. So choose x belongs to R. Okay, so here R means here the topological space is R. Space is R and the topology is the lower limit topology. So you have to understand that the topological space is R, not the RL, right? RL means we just denote the topology by the RL. That is that X tau, that pair we denote by RL. But here our topological space is R. Now let X belongs to R. Then choose beta X equal to that one. That is X comma X plus 1 by N, where N belongs to natural number. Now this forms a basis at X. Now for any open set U containing X, there exists N belongs to natural number such that X comma X plus 1 by N subset of U, right? That will imply beta X forms a basis at X and it is countable, right? Since beta X is countable, that implies the topological space R RL is first countable. So what is R? It is just the topological space X comma tau, right? Where X is just R and tau is that lower limit topology. Well, now this shows that RL is first countable. Now we prove that RL is separable. Now the next part, that is part 2. So we can call this is my part 1. Okay. Now for the part 2 we prove that RL is separable. That's mean we need to prove that R with the lower limit topology has a countable dense subset. So can you guess what is the dense subset? So this is just the rational number, right? Now claim Q, that is the set of rational number, is dense in RL. Why it is dense in RL? Because again, so let x be an arbitrary point in R and choose U be an open set containing X, right? Then there exists a basis element, say A comma B, such that X belongs to that A comma B subset of U, right? Now since A less than B, we can choose one rational number between A and B. Now choose one rational number, say Rx, such that A less than Rx less than B, right? It follows by the dense property in R, right? Then U, so we can say then Rx belongs to that AB subset of U. That implies U intersection Q, that is the set of rational number, is non-empty, and that will imply Q forms a basis for the topological space RL. Right? That implies RL is separable. Okay. Now for in the part 1 we have seen that RL is first countable. In the second part we have seen that RL is separable. Now the two parts left. One is RL is Lindelof and another part is RL is not second countable. Now I shall prove the not second countable first and then prove the Lindelof, because the Lindelof is not the easiest one. We have to do some work to prove that it is Lindelof. Now we prove that RL is not second countable. Okay, that's mean we have to prove that RL does not have any countable basis, right? Now if possible, or in other words, we can prove that RL has a basis beta and we will prove that beta is uncountable, right? Then we are done. So let beta be an arbitrary basis for RL. Okay. Now choose X belongs to R and choose open set X comma X plus 1 containing x. So we will choose an arbitrary element x and we choose one particular open set this containing x. Now since beta forms a basis, so there exists a bx belongs to beta such that x belongs to bx subset of x comma x plus 1. This. Now it is easy to see that x belongs to this open set and the least element is x, right? And x belongs to bx, which is a subset of this. That means the least element of bx is nothing but x, right? Now then, if x not equal to y, then for x we get bx, similarly for y we get by. Bx is not equal to by because the infimum, that is, you can say that least element as well, because here the infimum is the least element. But here I can write the infimum because the infimum of bx equal to x, which is not equal to y, equal to infimum of by. Now since the infimum of bx and infimum of by are not same, so bx not equal to by, right? Now that will imply there exists an injective map f from R to beta such that x going to bx. Now since R is uncountable, beta is also uncountable. Therefore, RL is not second countable. So by this part 1, part 2 and part 3, we have already proved that first countable does not imply second countable and the separable space does not imply the second countable topological space. Now in the part 4, we proved that RL is Lindelof, and this will solve the third one, that is, any Lindelof topological space may not be a second countable topological space. Okay, so now in the part 4, we proved that RL, that is the real line with the lower limit topology, is Lindelof. Okay, that's mean we choose one arbitrary open cover and then we find one countable collection, that is countable sub collection of that open cover which covers R. Okay, so let A be an open cover of R. Now let X belongs to R. Now since the collection script A covers R, so there exists A belongs to that script A such that X belongs to A, right? Now then there exists an a basis element X belongs to say A comma B, which is subset of A. We always get this kind of basis element, right? Now take for all of this collection, say B alpha, where alpha belongs to some indexed this, such that each A alpha comma B alpha belongs to some A alpha, where this A alpha belongs to A, and this collection and the collection, say this A dash covers R. Now this is always possible. Why? Because see, it is given that script A is an open cover of R. It is given, right? Now for each element X, we get an element A. We can take a different color. We can take an element A such that A belongs to script A and A contains the element X, right? Now since X belongs to A, so there exists a basis element, this kind of basis element such that X belongs to this basis element subset of A, right? That's mean for each element X we get a basis element this, which is subset of A. Now we take all such basis element, and obviously for each X we get a basis element. So if we take all such this kind of, that is for each X we get a basis element, right? And if we take all of this collection of this basis element, then that covers R. It is no doubt, right? And now it is given that each basis element contained in A, right here. So we call each A alpha B alpha subset of A alpha, right? Now here you note that if you have a different basis, suppose you have some A beta B beta and it is subset of some A beta, it may happen that A alpha and A beta are same. That's mean two different basis element may contain one single A alpha, right? This is true. That's mean now if we can show that this A dash, which is covers R, it has a countable collection which covers R, then we are done, because each of these basis element contained in a single A alpha. That's mean if we have a countable collection, say A alpha B alpha, this kind of, such that this is alpha equal to alpha 1 alpha 2, this, suppose we have a countable collection which covers R, then for each A alpha B alpha we can get A alpha, right? Then this collection A alpha 1 A alpha 2, this collection covers R, right? Okay, now we will do this mathematically. So first of all, okay, so take this again, the black color. Okay, now first of all, let the element C, that is the subset of R, which is union of this alpha belongs to this one, open A alpha B alpha, this one, right? Now this is a subset of R. Obviously this is a subset of R, no doubt of this one, right? This is subset of R. Now we claim R minus C, that C is countable. So we first prove that R minus C is countable. Why R minus C is countable? Because now choose an element X belongs to R minus C. Okay, take an element from R minus C. Now can you guess what will be that X which is R minus C? So this is my C take again a different color. So this is my C, right? Then what will be my R minus C? Now it is easy to see that then X equal to some A alpha dash for some alpha dash belongs to lambda, right? Why? Because see, just note that R covers by this set, right? R equal to union of all of this set where according to this, right? And C is the element of this, right? That's mean this is my R and this is my C, and that's mean we are constructing C by deleting some A alpha only, right? That's mean R minus C. Now that implies R minus C is observed from this A alpha dash. That implies X equal to A alpha dash for some alpha dash belongs to lambda, right? Now we prove that this type of X is countable. That's mean if we choose the collection, that is the set R minus C is countable. Why? R minus C is countable because see X equal to this kind of A alpha dash. Now choose a rational number Rx from this open set A alpha dash comma B alpha dash, which is subset of C. Fine. That's mean X. See, if we choose an element X from R minus C, since R is this equal to this and C is equal to this, that's mean X is just a boundary point. That is some type of A alpha dash, right? For some alpha dash. Now we take that interval whose boundary point is A alpha, that X, and we choose one rational number from that interval, Rx. Now similarly, for some Y belongs to R minus C, there exists Ry, right, which belongs to that kind of open interval, right? Now we claim if X less than Y, then Rx less than Ry. Now we claim that. Why? Because we know that X less than Rx, right? Because X is this boundary point, X is this boundary point, and Rx belongs to this interval, right? So X belongs to Rx, X less than Rx, and we also know that Y less than Ry, right? Now if possible Ry less than equal to Rx, then we will have X less than Y less than Ry less than equal to Rx. Now that will imply Y belongs to that open interval X comma Rx, which is subset of A alpha dash comma B alpha dash subset of C. This is a contradiction. Right? That's mean this will not be the case. So we have if X less than Y, then Rx less than Ry. Now this implies x not equal to y imply Rx not equal to Ry. Therefore, the map f from that R minus C to rational number forms that x going to Rx is injective. Right? Now since Q is countable, so R minus C is also countable. Right? Now we get R minus C is countable. We get R minus C is countable. Now what are the next part? Okay. Now since R minus C is countable, so for each x belongs to R minus C, we get an element, say A alpha x belongs to that script A, such that x belongs to A Rx. Right? Now this is my another collection, this one, which is just all of this say alpha x, where x belongs to R minus C. Now then this collection is this subset of A, right? Is a countable subcollection of A which covers R minus C. Right? So we get a countable subcollection of A which covers R minus C. Now we can tackle C. So what is my C? Now again go back to the formal definition. So this was my C, right? Union of these open intervals. Now see, given, not given, so by our construction, C equal to union of this A alpha comma B alpha, right? This is just a union of open intervals in R, right? Now this is subset of R. Now take the subspace topology on C induced from the usual topology of R. That's mean C is union of this type of open interval, and we know these are just a type of open interval in R, that is in the usual topology. So we consider R as a usual topology and we take the subspace topology in C. Then C is covered by this kind of open set, A alpha, B alpha, alpha belongs to lambda, covered by the collection, right? The collection this, which is an open cover in usual topology of R. Now we claim that C is Lindelof. So why C is Lindelof? Okay, first of all, we know that R with usual topology is second countable. Right? We have seen that this is second countable. Now since R with usual topology is second countable and C is a subspace of R, now since C is a subspace of R, that implies C is also second countable. Right? We have seen that any subspace of a second countable topological space is also second countable. That's when C is second countable. Again, we have also seen that is, we have proved that every second countable space is also a Lindelof topological space. Right? Now that will imply C is Lindelof. Right? That's mean we proved that C is Lindelof. Remember, we cannot use the fact that R is Lindelof, that will imply C is Lindelof. We cannot use that fact. Why? Because the subspace of a Lindelof topological space may not be a Lindelof topological space. We will prove that later. That's why we cannot use that kind of result, that because that is not true. So we have to come via this way. That's mean R is second countable. Now C being a subspace of R is also second countable. Now since second countable imply Lindelof, so C is Lindelof in usual topology, right? Now since C is Lindelof in the usual topology, we can specify that one, otherwise Lindelof in usual topology. Usual topology. That's right. Now C is Lindelof. Now since C is Lindelof, so we have a countable subcollection of this which covers C. Now that will imply there exists a countable subcollection. This one A alpha, B alpha, for alpha equal to alpha 1, alpha 2, this one which covers C, sorry, not this one, this one, this covers C, right? Now since this kind of union of open set covers C, now we can back to our lower limit topology. That will imply if we take this collection A alpha comma B alpha, where alpha equal to alpha 1, alpha 2, this also covers C, right? Now since that A alpha comma B alpha subset of A alpha, where A alpha belongs to that script A. Now let's call it A double dash, which is that collection of all of this A alpha such that alpha equal to alpha 1, alpha to this, which is subset of this. Sorry, call it a triple dash, as we used the a double dash before, right? Now a triple dash subset of A, and this covers C. Why this covers C? Because each of the element of a triple dash is A alpha, and each of the A alpha contains that A alpha, B alpha, that interval, and this kind of open interval, that collection covers C. That means a triple dash, which is subset of A, that is script A, covers C, and this is a countable collection. Now we have that a double dash subset of A is a countable collection which covers R minus C, and a triple dash, which is subset of again A, is a countable collection which covers C. Now that will imply that a double dash union a triple dash is a countable subcollection of A which covers R in the lower limit topology. Right? That implies RL is Lindelof. Now we prove that product of separable spaces is also separable, but the product of Lindelof spaces may not be Lindelof. So first of all, one theorem. So product of separable spaces is also separable. Now the proof is very simple. So let X and Y be two separable spaces okay. So let D1 and D2 be two countable dense subset of X and Y respectively. That implies D1 closure equal to X and D2 closure equal to Y, and D1 and D2 both are countable. Now that will imply D1 cross D2 is also countable, right? Now what we can do, now we prove that D1 cross D2, this closure equal to X cross Y. y. So let x cross y belongs to that capital X cross y, that is from the space. Now let u cross v be an basis element in X cross y containing the points X and Y, containing the point X cross Y, right? That imply X belongs to U and Y belongs to V. Now since D1 and D2 are dense subsets of X and Y respectively, that imply D1 intersection U is non-empty and D2 intersection V is also non-empty. Now that will imply D1 cross D2 intersection U cross V, this is also non-empty, right? Now that will imply D1 cross D2 is dense in X cross Y. Now we shall prove that the product of two Lindelof spaces may not be a Lindelof space. This is the theorem. Actually, we will give one counter example. That's mean we will give one example which is Lindelof, but its product, that is if we take two copies of the Lindelof space, that is not Lindelof. So my counter example is RL cross RL. So we prove that RL, that is the real line with the lower limit topology, is Lindelof. Right? Now we claim that RL, product RL is not Lindelof. See, just remember this plane and the example, because this is a very important counter example in topology. So here this example will serve for many purposes, and you will see in the future as well that topological space RL cross RL. Okay. Now what is my RL cross RL? This is just a R with the lower limit topology and then take the product. That's mean any basis element of RL cross RL is of the form this A, B, product with C, D, right? That's mean this kind of rectangle, this part is open, so this is my A cross C, this is my A cross, this is my C cross not C, B cross C, right? And this is my A cross D, this is my B cross D, right? Okay, this part is open and this part is closed. Okay, now this is my plane. Okay, now consider this diagonal. Say this diagonal. So let D is the diagonal which is my x comma minus x, where x belongs to R. Then D is a subspace in that RL cross RL, right? This diagonal. Now it is easy to prove that the complement of D is open, right? That is, if we take D, this is my D. The complement of D is this plane and the lower plane, right? Now the complement of D is open. It is easy to prove that, because if you take any element, say here, then we can always get this kind of rectangle, right? Even if we have any point here, we will always have this kind of rectangle, right? Even if we have very close to this, again we can take this point and this, and we can find this kind of rectangle. Even if we have point very close to this, still we can get one rectangle which is this kind of, right? This kind of, right? So it is easy to see that R cross R minus D is open. Open where? In RL cross RL, right? Now we take the cover. So let this A be the cover of this kind of, say, x comma x plus 1 product with minus x comma minus x plus 1. This one where x belongs to R. Take this, call this is A dash. That's mean for each of this point in the line, say this is my x comma minus x, right? So this is my point x cross minus x, or you can write so this is my point x cross minus x, right? Then we will choose this x plus 1, that is this plus 1, minus x plus 1, this and this ball, right? Now this open set containing x cross minus x, right? And it will intersect the diagonal in exactly one point. So if this is my x, here x is negative, so minus x is positive, it is fine. Now this is plus, and this is my rectangle, this one, right? Now let that open cover A is A dash union my R cross R minus D, this. Then obviously A is an open cover of R cross R. You can write here RL cross RL if we want to specify the topology, right? So where each open set in A, so other than the open set R cross R minus D, if we take any open set in A other than this, intersects D in exactly one point. Right? Why? So we have done this, right? So if we take any point this, so this is my rectangle, so this is my rectangle, and this will intersect this D in exactly one point, this point, right? Okay. Fine. Now then A does not have any proper subcollection which covers R cross R, right? Because A has the one element is this one, that is that complement of this diagonal. This is the one element, and other element intersect the diagonal in exactly one point. That's mean we cannot remove any one of the element from A, right? So A does not have any proper subcollection and A is uncountable. So RL cross RL is not Lindelof. That's mean we have a collection A which is uncountable, right? And it does not have any subcollection which covers R cross R. That's mean RL cross RL is not Lindelof. Remember that here why we use that R cross R, because my topological space is R cross R, but we have given a topology which is the lower limit topology product with lower limit topology, right? So RL cross RL is just my x comma tau, where x is my R cross R and tau is the product of lower limit topology. Lower limit topology. So now we prove that subspace of a separable space may not be a separable space. So here is the theorem. So subspace of a separable space may not be separable. Again, we give one counter example. Again, my example is RL cross RL. So, consider the topological space that RL cross RL. Okay. Now consider this topological space. Now we know that RL is separable. Now we know that RL is separable, right? And we also know that product of two separable spaces is separable. Now since product of two separable spaces is separable, that imply RL cross RL is separable. Now, can you construct one subspace of this separable topological space which is not separable? Now, the example is simple, same as before. Now, consider the diagonal D, that one, that is x cross minus x, where x belongs to R. Consider this subspace of RL cross RL. Now consider this subspace. Now we know that for each point x comma minus x cross minus x belongs to D, the open set U, which is just say x plus 1 comma x plus 1 product with minus x comma minus x plus 1. Now if we take this open set, then this open set intersects D in exactly one point, right? Point, namely x cross minus x. We can see the picture again. So this is my RL cross RL, that is R cross R with the product of lower limit topology, and this is my diagonal D. Now if this is my point x cross minus x, then this open set intersect, if this is my U, then this open set intersect D in exactly one point, right? Okay, that imply in subspace topology D forms a discrete topology. In other words, we can say that as a subspace of RL cross RL, D has discrete topology as each singleton point x cross minus x can be written as D intersect the open set U, right? So x comma x plus 1 cross minus x comma minus x plus 1, right? So D has a discrete topology. Now since D has discrete topology, so D is not separable. The subspace of a separable space may not be a separable space. Now similarly, we can prove that the subspace of a Lindelof space may not be Lindelof. Okay. Now, can you give one counter example for this? That's mean you have to give one example which is Lindelof, but its subspace is not Lindelof. Now, the example is, consider the ordered square. That is I2O, which is just 0, 1 cross 0, 1 with dictionary order topology. Now, why this is Lindelof? We know that this is compact, right? So, being an linear continuum, this ordered square is compact and hence Lindelof. We know that, right? Any compact set is Lindelof, because if you take any arbitrary open cover of the ordered square, now since it is compact, so it has a finite subcover which covers the ordered square, right? Now since it has a finite subcover, so it is also countable, right? So any compact set, we know that any compact set is Lindelof. So ordered square, since it is compact, so it should be Lindelof. But we can construct one subspace of the ordered square which is not Lindelof. Just take Y equal to the topological space 0, 1 cross open 0, 1. This one. That's mean we have this order. This was my ordered square. So 0 cross 0, 1 cross 0, 0 cross 1, 1 cross 1. Now we have taken all of this strip. This one. So we have taken all of this possible stripped for each x. We consider this. right? Now then, y equal to just union of x belongs to 0, 1. It is union of x cross 0, comma x cross 1, right? That's mean y is union of disjoint, that is arbitrary number of, we can say uncountable number of disjoint open sets. Then obviously you cannot remove any one of them, right? Then if we consider this is my collection, that x cross 0, comma x cross 1, x belongs to 0, 1, then this is an open cover of y, but it does not have any proper collection, any proper sub-collection which covers y. That's mean the collection A is uncountable and we cannot remove any of them, right? So y is not Lindelof. Therefore, we prove that product of two separable spaces is separable. We prove that subspace of separable space may not be a separable space, and we prove that product of two Lindelof spaces may not be Lindelof, and we also prove that subspace of Lindelof space may not be a Lindelof space. So these are all about for today. So in the next lecture I shall start the separation axioms.